Hello everyone, welcome back to Diksha Karnataka YouTube channel, and in the second PU midterm series today I am going to discuss the second chapter, Electrostatic Potential and Capacitance chapter. This will be the theory division where I am going to revise all the important concepts quickly so that you can revise the chapter without wasting too much of your time. So let's start with the basic list of contents. What are we are going to cover in this lecture? So electric potential and potential energy, then we have equipotential surface and electric field, the relationship between them. We have electrostatics of conductors, we have capacitors, and that's it. That is the last topic. Now let us start with electric potential energy. So what is the meaning of potential energy? The basic definition of potential energy is same as that you have learned in your class 11th, that is work done when you do some work in some conservative field. The energy that is stored in the object is basically the potential energy. So whenever you are doing some work in a conservative field, very important, the force must be conservative. For example, gravitational force is a conservative force, electrostatic force is a conservative force, whereas one common example which is not conservative is friction. In case of friction, whatever work you do does not get stored, so that energy is completely lost. But if the force is conservative, the work that you are doing will be stored as the potential energy. So if you are doing ಸ್ವಲ್ಪ hard work right now, that will reflect in your marks in the second PU midterm exam as well as in the final exam. So that will be stored as your potential energy, right? So let's look into the basic definition. So work done to move a charge in an external electric field applying some external force is the potential energy. So this work is done against the electrostatic force and gets stored as potential energy. So in electrostatic field, if you are doing some work against the electric field, for example here it is positive, if you bring the charge closer, then it will be a positive work. If you move the charge away, then you yourself is not doing any work, the field is doing the work, that means the work done will be negative. So here the basic definition of potential energy, and we are mostly interested in the difference of potential energy rather than the exact potential energy. So when you move a charge from point A to point B, whatever work you are doing, WAB, that represents the difference in potential energy of point A and B. Okay, now let's continue. Electrostatic potential is equals to potential energy per unit test charge. Now we are defining electric potential. Similar, remember that Coulomb force and electric field. Coulomb force was between two charges, whereas electric field is only due to one charge. So you have to eliminate one single charge by dividing it. So electrostatic potential is basically potential energy per unit test charge. So if the test charge is unit, that means you have divided the work done by the charge that you are moving, that will give you the potential energies. For example, potential is basically given by the work that you have done to move divided by the charge. Okay, so delta V is equal to delta U by Q. And again we generally mention in terms of delta V, that is the difference in potential. Exact potential we will calculate in many cases, but mostly we are interested in potential difference. Work done by an external force in bringing a unit positive charge from infinity to a point is the electrostatic potential at that particular point. It is the absolute potential, definition of absolute potential. And the derivation is there. We will do the derivation in the 2-5 marker section, 2-3-5 marker section. So don't forget to watch that as well. So basically when you bring a unit positive charge from infinity to a point in electric field, whatever work that you are doing, that is called the potential of that point. So you started your journey at class 1 or maybe lower KG, and then you are continuing your work till you have reached your class 12th. So entire work that you have done starting from your lowest grade till now, lowest class till now, that energy is stored within you as your potential energy. Potential energy and potential are not the same. Okay, obviously if you multiply potential with the charge, test charge, you get the potential energy. Similarly, if you divide the potential energy by the test charge, you will get the electric potential. Work done to bring a unit positive test charge from a point A to point B is called the potential difference between the points. In the next chapter, current electricity, potential difference takes the main stage. That is the main important thing. If the work done by the external force is positive, then the potential difference is positive. If the work done by the external force is negative, then the potential difference is negative, right? So if you move from low potential to high potential, that means you are doing work, but if the object is coming from high potential to low potential, then the work done will be negative. Now this is the definition of potential due to a point charge. This is the derivation. The derivation, as I said, we will be doing in the derivation section, but if you see that potential is inversely proportional to the distance. Potential is inversely proportional to the distance. There is one more small mistake here. What mistake? That we have mentioned here capital Q, so this will also be capital Q. Okay. The same equation is applicable for any point outside the charged spherical shell. So if you have a charged spherical shell, okay, we have already calculated the electric field. So any point outside charged shell, we have already calculated the electric field. Similarly, this formula is valid for a charged spherical shell having charge Q. Okay, point outside. Potential inside the shell will be constant. So there is only one difference, that potential inside the shell is constant. Now there is a small question for my audience, is that what will be the potential at the exact point where charge is located? Okay, for spherical shell outside it is equals to this equation, inside it is constant. So basically it is well settled for a spherical shell, but for a point charge, what will be the electric field exactly at the point of the charge? You can use this equation and find that out and mention the answer in the comment section of the video. Now if you see that E and V comparison graph, that E basically starts at a higher value and falls rapidly, because E is proportional to 1 upon R square, whereas V is proportional to 1 upon R. So it starts with a higher value, but it falls rapidly, whereas V proportional to 1 upon R, okay, this axis is representing R, okay, obviously this axis represents R, okay, it starts at the little bit smaller value, but it goes to 0 also very slowly compared to E. So E falls to, this is E graph, okay, it goes to 0 quickly, whereas V is still not 0. Okay, if you stretch the graph, they will meet 0. So 1 upon R square goes to 0 quickly compared to 1 upon R. Now next, potential due to a dipole. So potential due to a dipole at any point on space is given by 1 by 4 pi epsilon naught P cos theta by R square. So this is the basic definition of potential due to a dipole. So in case of electric field, we have calculated two different positions, but for potential it is an arbitrary any position, and it is given by P cos theta by R square. So normally electric potential is proportional to 1 upon R, but due to a dipole it is 1 upon R square. Similar to that of electric field, normal electric field is 1 upon R square, but due to a dipole it is 1 upon R cube. So remember that for dipole it is always the power of R is generally one step higher than that of the normal case. So electric potential normally 1 upon R, due to a dipole it is 1 upon R square. Electric field due to a dipole is 1 upon R square, whereas due to a dipole is 1 upon R cube. Now, an equipotential surface is a surface with constant value of potential at all points on the surface. Now, let us discuss a little bit more about equipotential surfaces. So, if you see a equipotential surface due to a point charge, we know that if the distance is constant, potential is constant. It is proportional to 1 upon r. Now, charge is constant here. So, V will be constant and V is a scalar quantity. Mind it, V is a scalar quantity, unlike electric field. Electric field is a vector quantity, but potential is a scalar quantity. So, if you go to a distance, okay, all the circles that you can draw, in fact all the sphere you can draw, concentric spheres, because it is all the points on this sphere are equal distance, they will be at equal potential. They will be at equal potential, and this is called equipotential surface. For any charge configuration, equipotential surface through a point is normal to the electric field at that point. So, if you consider the electric field, what is the direction of electric field? Electric field is radially outward. Now, if you consider this point, what will be the electric equipotential surface? Equipotential surface is this one, right? Tangential surface, curved, for curved we consider the tangent. So, it is always normal. Electric field and equipotential surface are always normal to each other. Okay, and also work done to move a charge in the equipotential surface is 0. If you want to move a charge, suppose this is a equipotential surface, okay, if you want to move a charge within the equipotential surface, the work done will be 0, because work done basically represents potential difference times charge. Okay, work done represents potential difference times charge. That's why work done will be 0, because potential difference is 0, because it's a equipotential surface. Now, relationship between electric field and potential, very important derivation as well. E equals to minus dV by dl. So, here it is electric field, and the negative sign represents that as electric field increases, V decreases. Okay, the direction of E is in the direction of decreasing V. Okay, direction of E in the direction decreasing V. So, if V is, suppose we have 2 points, okay, A and B. Electric field, suppose V is higher here and V is lower here. Negative represents V is lower. So, the direction of electric field will be from higher V to lower V. So, that is the direction of electric field. That is why there is a negative sign. Electric field is in the direction in which the potential decreases the steepest. That means the direction where electric potential decreasing faster. Electric field is normal to the equipotential surface at that point. We already discussed it. Now, system of charges. So, for system of charges of 3 charges, electric potential is important to calculate, not E. It will be electric potential energy. Okay, suppose we have 3 charges Q1, Q2 and Q3. The potential energy of the system will be given by 1 by 4 pi epsilon naught Q1 Q2 by R12, Q1 Q3 by R13, Q2 Q3 by R23. Okay, this is a formula for numerical question. Final expression for U is independent of the way the configuration is assembled. The potential energy is given by the present state of configuration and not the way the state is achieved. So, in this case, it does not matter if you brought Q1 first, Q2 second, Q3 last. It does not matter on that. It only matters the final configuration, the final distances, okay, because it's a conservative force field. So, ultimate final position is important, not how it is achieved. Potential energy in an external field, single charge. Okay, when a charge is placed in an external electric field, the potential energy of the charge is given by U is equal to Q into V. I already mentioned that once. Here V is the electric potential at that point. Two charges, what about two charges? When two charges Q1, Q2 are placed in an external electric field, the potential energy of the system is given by U equals to Q1 Vp plus Q2 Vq plus 1 by 4 pi epsilon naught Q1 Q2 by R. What is the meaning of that? Suppose we have two charges P and Q, 2 points are there. Here the potential is Vp, here potential is Vq, charge kept here is Q1, charge kept here is Q2, then this is the formula for total potential of the system. Important for numerical question. Now electric dipole. So when you keep an electric dipole in an external electric field, okay, the potential is given by Pe cos theta. So Pe cos theta, in fact there is a negative sign, minus Pe cos theta is the potential energy of the system. P is, what is P by the way? P is the dipole moment. Now let us look into the electrostatics of conductors. Few points that you have to remember. What are the points? Metallic conductors contains mobile charge carriers, namely electron. Already know that. Any metals contain free charge carriers which can carry charge from one point to another, and they are called electrons. Okay, next is these electrons are free within the metal but not free to travel out of the metal. So basically what does that mean? That means you are in a house arrest, right? You may have faced that your parents are going out and they locked the room from outside. They are asking you to study at your room, but what you are doing, instead of studying in your room, you are roaming around from one room to another. You are watching TV, playing games on the mobile or tablet, right? So you are doing that. You are free within the house but you are not allowed to go outside the house. Similar thing is for electron. He is in a house arrest. He can travel anywhere within the metal but he cannot leave the metal. The free electrons from a kind of gas, they collide with each other and with the ions and move randomly in different directions. So basically it is called electron gas. Electron gas means it is behaving like an ideal gas. You have studied ideal gas. So they are behaving like ideal gas. They are colliding with each other. They are moving in the random direction, okay, in the absence of external electric field. Next, in an external electric field, they drift against the direction of the field. We will discuss more about this in the next chapter. So if you apply an electric field, the electrons move in the opposite direction of the electric field. So if there is an electric field present in the metal, the electrons start moving in the opposite direction. That is the nature of the electron. It is negative charge. So negative charge always moves in the opposite direction. Now few points to remember. Inside a conductor, electrostatic field is always 0. Electric field is always 0. Potential is constant. The interior of a conductor can have no excess charge in the static situation. So inside the conductor there will be charges, but total number of positive charge will be equals to total number of negative charge. So if you charge a conductor, all the charges will be always outside, all the extra charge that makes the metal charged. Okay, it will always stay outside, be it positive or be it negative, it will always stay on the outside. For example, if you take a plastic ball, if you put it in the water, it will always come up and it will float. So the charges are plastic balls and metal can be considered to be like water. Okay, so charges will always float on the surface. Even if you try to push it inside, after some time it will come up and it will float again. Okay, now if you apply an external electric field, what will happen is that the negative charges will move opposite to the electric field and the positive charges will move in the direction of electric field, and there will be exactly equal and opposite electric field developed in the metal so that no field can pass through the metal. So the net field inside the metal will always be 0. Be it charged, be it placed in an external electric field, the electric field inside a metal will always be 0. At the surface of the charged conductor, electrostatic field must be normal to the surface at every point. So, electrostatic field will be normal to the surface at each and every point. Now, let us move into the capacitor. So, conductors are done. There is one more property of conductor which is called electrostatic shielding. Because the electric field inside a conductor is 0, we use it for a very important property which is called electrostatic shielding. High level and higher value and very sensitive instruments are kept in a metal cages, so that there are no external influence or external interference with that particular system. For example, the weather machine or say seismograph, they are kept in a metal cages most of the time. Some high-end devices such as MRI device, okay, they are kept in metal. The outer layer or outer cover of the room is generally made of metal, so that no external electric field can disturb the result of that device. There are many other devices which are housed or kept inside metal containers. Now, let us discuss about capacitors. What is the role of a capacitor? Capacitor is a device that used to store charges. Basic property of basic use of capacitor is to store charges. It provides a constant voltage. Okay, capacitor is a system of two conductors separated by an insulator. So, two conductors, if they are separated by insulator, are called a capacitor. Usually in practice, the two conductors have charges Q and minus Q with potential difference V equals to V1 minus V2 between them. So, there is a potential difference, there is some charges. So, generally capacitors are, I will show one diagram, but capacitors are generally represented like this. If the charge on this plate is Q, charge on the other plate will be minus Q. Okay, it is always the case. Total charge inside a capacitor is always 0. Total charge is always 0. But if we mention charge of a capacitor, that means the highest charge that is there in one of the plates. One of the plates, magnitude of highest charge kept in one of the plates, that is the meaning of charge of a capacitor. But total charge, if the question comes, very very important, if question comes the total charge in a capacitor, answer will be 0. Okay, Q is called the charge of the capacitor, though in fact the charge on the one of the conductors, the total charge of the capacitor is 0. The electric field in the region between the conductors is proportional to the charge Q. That is, if the charge is on the capacitor say doubled, the electric field will also be doubled. So, the charge basically stored in the form of electric field. If you increase the charge, electric field will also increase. Consequently, V is also proportional to Q, and the ratio of Q by V is a constant. For a capacitor, the ratio of Q by V is constant, and that is called capacitance of the capacitor. The constant C is called the capacitance of the capacitor. C is independent of Q or V. Even though the formula says it depends on Q and V, basically it's a constant. Q and V ratio is a constant, so it does not depend on Q and V. It depends on certain things but not on Q and V. The SI unit of capacitance is farad, and farad is basically equals to coulomb per volt. Coulomb per volt. Coulomb per volt. Unit of potential is volt. By the way, if you have missed it, the capacitance C depends only on the geometrical configuration, shape, size, separation of the system of the two conductors, and the type of insulating medium between the conductors. So, it depends on the shape, size, area, and what you have kept inside the capacitor. That is the major thing. It is independent of charge and voltage. We have seen some new MCQ questions from this concept. From the above equation, we can see that large the C, V is small for a given Q. So, if you keep the C high, okay, the V can be controlled even using small amount of Q. You can keep a higher V or lower V. Okay, this means that capacitor with large capacitance can hold a large amount of charge Q at a relatively small V. This is of practical importance. So higher capacitance means it can store higher charge even if the voltage is low, right? So here is the diagram of the capacitor. High potential difference implies strong electric field around the conductors. A strong electric field can ionize the surrounding air. The charges produced due to ionization are accelerate towards the oppositely charged plates. This partly neutralizes the charge on the capacitor plates. The charge of the capacitor leaks away due to the reduction in the insulating power of the intervening medium. So if you keep a lot of charge between the plates, what happens is that some of the charges will leak from positive to negative. Okay, some electrons will move from negative charge plate to positive charge, because this is called electric leakage. Okay, because of the leakage some charges will leak into from negative to positive, and overall charge of the capacitor plates will reduce. The maximum electric field that a dielectric medium can withstand without breakdown is called dielectric strength. This is also very important for fill in the blanks question. The dielectric strength of air is about 3 into 10 to the power of 6 volt per meter. Important for MCQ. This value is important for MCQ. For a separation between conductor of order 1 centimeter or so, this field corresponds to a potential difference of 3 into 10 to the power of 4 volt between the conductors. There is a limit to the amount of charge that can be stored on a given capacitor without significant leaking. In practice, a farad is a very big unit. Okay, farad is like, if you consider a spherical capacitor, okay, this type of capacitor, it can be shown that to have 1 farad capacitance, its size would be bigger than that of the earth. Okay, you have to construct a huge sphere to store to have 1 farad capacitance, right? So that is almost impossible to have. You cannot construct a capacitor which is double or bigger than the size of the earth. So farad is a huge unit. In practice we will use the units are microfarad, that is 10 to the power of minus 6, nanofarad 10 to the power of minus 9, picofarad 10 to the power of minus 12. So these are the most commonly used capacitors. Here is a diagram of different values of capacitance. Now, parallel plate capacitor. In a parallel plate capacitor consists of 2 large plane parallel conducting plates separated by a small distance. 2 large parallel plates obviously separated by a small distance. And its capacitance is given by A epsilon naught by D. This is sufficient for PU board. For KCET we have to add the dielectric constant as well. Okay. Now combination of capacitors, based on this we have seen numerical questions. So what is series combination? Series combination is when one capacitor is connected after another. Okay, and if 2 capacitors are there, mostly 2 is sufficient. There will be combination of capacitors, but series combination maximum 2 will be there. So you have to remember that the equivalent capacitance is given by C1 C2 by C1 plus C2 for 2 capacitors. For more than 2 capacitors, the formula is C equivalent equals to 1 by C1 plus 1 by C2 plus 1 by C3 ... Now remember that when you calculate the right hand side, on the left hand side you have to take reverse to get the value. You have to take inverse of both sides, okay, or reciprocal on both sides. I have seen students, they calculate the right hand side properly, then in the next stage they directly write the C equivalent equals to the same value. Suppose you calculated here, you got the value say 2, so C equivalent will be 1 by 2. But I have seen students making mistakes. After solving it, they write C equivalent equals to 2, which is wrong. Okay, so be careful. That's why I prefer this formula for 2 capacitors. Now parallel combination of capacitors is most easy. When in parallel combination, remember that in series combination the charge is same, voltages are different. Okay, in parallel combination the charges are different okay, but voltage is same. And in parallel combination you can have as many as you want. The formula is easiest. Okay, the equivalent capacitance is given by C1 plus C2 plus C3 and so on. Okay, here charges are different, but voltage is same. Okay, now few more formulas. Energy stored in a capacitor. What is the common formula for energy stored in a capacitor? Energy stored is given by half CV square. Okay, this is the most common formula. There are few more variations, half Q into V, okay, and Q square by C, but you can use this form. This is the most easiest formula. And another formula is that energy density of electric field, that is the energy density of a capacitor, which is given by small u. This is capital U, that is the total energy. Small u is the energy density, which is nothing but U by A, which can be shown to be half epsilon naught E square. The derivation is not important, but the formula is. Okay, so U is equal to half epsilon naught E square is the energy density of a capacitor. Now this is the end of this lecture. It is a short revision. Quickly, I hope this helps, and if you have found this useful, please don't forget to like this video and subscribe to our channel. Also join our WhatsApp channel to get the PDF of this lecture. I will be back with the MCQ and fill in the blanks from this chapter. Till then, bye.